There's something almost magical about the idea of a particle so stealthy, so utterly indifferent to the world around it, that it can slip through an entire planet like a whisper in the wind. These are neutrinos, nature's ghostly messengers, streaming through the cosmos in uncountable numbers, yet so elusive that they defy detection. Every second, trillions of them pass through your body without a single interaction, as if you weren't even there. It's a thought that borders on the surreal, and yet, it's this very invisibility that makes neutrinos one of the most fascinating puzzles in modern physics. Today, we're diving deep into what scientists call the ghost particle conspiracy, a mystery that stretches from the heart of exploding stars to the very fabric of our universe. What if I told you that these tiny, nearly massless particles hold clues to some of the biggest questions in existence? How galaxies form, why matter dominates over antimatter, even the fate of the cosmos itself, neutrinos are quietly shaping it all. Their story begins in the violent cores of supernovae, where they're born in unimaginable numbers, and it winds through underground labs where scientists chase their shadows with detectors buried deep beneath mountains. But here's the twist: neutrinos don't play by the rules we expect. They oscillate, change identities, and refuse to be pinned down, forcing us to rewrite the textbooks. It's as if the universe is teasing us, offering glimpses of a deeper truth just out of reach. This isn't just a tale for physicists. It's a cosmic detective story that challenges our very understanding of reality. Imagine a particle that can travel billions of light years without slowing down, carrying secrets from the distant past. Or consider this: without neutrinos, the universe as we know it might not exist at all. They're the unsung architects of cosmic evolution, and yet for decades they've slipped through the cracks of our awareness. So why should you care? Because unraveling the neutrino enigma isn't just about filling in gaps in a textbook. It's about uncovering the hidden forces that sculpted everything from the atoms in your body to the vast emptiness between galaxies. Buckle up, because we're about to journey into the heart of one of nature's greatest mysteries, where the answers might just rewrite everything we think we know. To understand the birthplace of neutrinos, we have to step into the chaos of a dying star. Picture a supernova, an explosion so powerful it outshines entire galaxies for weeks. Deep in its collapsing core, protons and electrons are crushed together with such force that they merge into neutrons, releasing a flood of neutrinos in the process. In just a fraction of a second, more neutrinos pour out than there are stars in the observable universe. These particles don't just escape, they blast through the collapsing star's outer layers like a cosmic tsunami, carrying away 99% of the supernova's energy. That's how vital they are. Without neutrinos siphoning off that energy, the explosion might fizzle out entirely, leaving no heavy elements behind to form planets or life. But supernovae aren't the only neutrino factories. Look inside our own sun, and you'll find a quieter but ceaseless production line. Every time hydrogen fuses into helium in the sun's core, neutrinos are born as byproducts, about 65 billion of them streaming through every square centimeter of Earth every second. These solar neutrinos are like cosmic breadcrumbs, offering a direct glimpse into the nuclear furnace that's been burning for 4.5 billion years. Scientists once panicked because they detected only a third of the neutrinos predicted by theory, until they realized the particles were shape-shifting mid-journey, a discovery that earned the Nobel Prize. Then there's the ultimate neutrino origin story, the Big Bang. In the universe's first second, a primordial sea of neutrinos flooded space, relics so ancient they've been cooling undetected for 13.8 billion years. If we could catch just one, it would be a time capsule from the birth of everything. Even black holes get in on the action, spewing neutrinos as they rip apart stars or collide in gravitational waves. Each source imprints its own signature on these particles, turning them into coded messages about the universe's most extreme environments. The wildest part, we're only beginning to crack their secrets. Every neutrino detected is like intercepting a letter from a place we can never visit, written in a language we're still learning to read. The nickname ghost particles isn't just poetic flair. It's a perfect description of how neutrinos defy everything we know about matter. Picture standing in a hurricane while countless raindrops pass right through your body without ever touching you. That's the reality of neutrinos, except instead of raindrops, it's trillions upon trillions of these particles every second. They move through solid rock, oceans, even entire planets as if nothing were there at all. This isn't just rare, it's fundamentally different from how any other particle behaves. While electrons buzz around atoms and photons bounce off surfaces, neutrinos exist in their own ghostly realm, barely acknowledging the universe they're passing through. What makes them so elusive? It all comes down to their refusal to play by the rules of electromagnetism, the force that governs most everyday interactions. Unlike electrons that create sparks or protons that form atomic bonds, neutrinos carry no electric charge. They only respond to two of nature's four fundamental forces: gravity, which is laughably weak on their tiny scale, and the nuclear weak force, which operates at vanishingly short ranges. This means they can sail through a light year of lead without a single collision. In fact, the average neutrino could pass through a block of solid iron stretching from Earth to the Moon and still have a 50-50 chance of making it out the other side untouched. This ghostliness isn't just a curiosity, it's what makes them cosmic of information. While light gets absorbed, scattered, or distorted traveling across space, neutrinos arrive pristine, carrying unfiltered stories from the universe's most violent events. When a star explodes in a distant galaxy, its light might take centuries to reach us through cosmic dust, but its neutrinos cut straight through, delivering a clean signal of the explosion's very first moments. Modern detectors are like ghost hunting equipment, waiting years just to catch a handful of these phantoms. The famous IceCube observatory in Antarctica uses an entire cubic kilometer of glacial ice as its detector, relying on the rare occasion when a neutrino finally interacts and creates a flash of blue light. The irony, the very property that makes neutrinos so valuable, their reluctance to interact also makes them maddeningly difficult to study. It's like trying to decipher a message written in vanishing ink. Every detection is a small miracle, requiring instruments of staggering sensitivity. Some experiments use vats of liquid that flash when a neutrino, against all odds, bumps into an atomic nucleus. Others watch for the faint trails neutrinos leave in ancient or deep underwater. Each method pushes technology to its limits, all to catch glimpses of particles that treat the entire Earth as if it were made of mist. Yet this ghostly nature might hold the key to their cosmic importance. Because they barely notice matter, neutrinos were among the first particles to decouple after the Big Bang, streaming freely through the newborn universe. They may have subtly shaped how galaxies clustered together in the early cosmos. Even now, they could be carrying evidence of phenomena we've never dreamed of: dark matter interactions, hidden dimensions, or cracks in our understanding of physics itself. The next time you feel the sunlight on your skin, remember, trillions of solar neutrinos are passing through you that very second, utterly unnoticed. They're the universe's silent witnesses, and we're only beginning to learn their language. Catching a neutrino is like trying to trap a shadow with your bare hands, an exercise in near-impossible precision. Scientists have had to build some of the most ingenious, sprawling experiments in human history just to stand a chance. Take the IceCube Neutrino Observatory, buried over a mile deep in the Antarctic ice. It's not just a detector, it's an entire frozen telescope, using a cubic kilometer of pristine ice as its hunting ground. When a neutrino finally, miraculously interacts with an atom in the ice, it creates a fleeting burst of blue light called radiation. That tiny flash is the ghost's footprint, and IceCube's thousands of embedded sensors wait patiently, like a net cast into the cosmic dark, hoping to snag one of these elusive particles. But why bury detectors underground or underwater? It's all about filtering out the noise. Earth's surface is bombarded with cosmic rays, high-energy particles that create false signals. By placing detectors deep beneath rock or ice, scientists create a natural shield. The overlying material absorbs most cosmic rays, while neutrinos, true to their ghostly nature, pass straight through. Super in Japan takes this idea even further. Housed in an abandoned mine, its detector is a stainless steel tank filled with 50,000 tons of water, lined with sensitive light detectors. When a neutrino interacts with a water molecule, it can produce a faint ring of light, a whisper of its presence. The scale of these experiments is staggering, but so is their sensitivity. Some detectors can pinpoint a neutrino's direction to within 1 degree, tracing it back to its cosmic source like following a breadcrumb through the void. Others, like the upcoming deep underground neutrino experiment in South Dakota, will shoot artificial neutrino beams through 800 miles of Earth to study how they change flavor mid-flight. It's a testament to human ingenuity, building cathedrals of science just to catch particles that treat the entire planet as if it weren't there. And yet, for all this effort, success is measured in handfuls. Even the largest detectors might only catch a few neutrinos per day from a nearby supernova. That's why every detection feels like a triumph, a brief crack in the neutrino's armor of invisibility. These rare moments have already revolutionized physics, confirming that neutrinos have mass, revealing their shape-shifting nature, and even offering clues about the imbalance between matter and antimatter in the universe. Each flash of light in the darkness isn't just data, it's a message from the heart of a star, the edge of a black hole, or the dawn of time itself. The detectors we build today are more than machines, they're translators, decoding the universe's quietest language. The sun has been playing a cosmic shell game with us for decades, hiding its neutrinos in plain sight. Every second, our star's core acts like a colossal neutrino factory, where the fusion of hydrogen into helium churns out these ghostly particles in unimaginable numbers. Yet when scientists first tried counting them in the 1960s, something didn't add up. Their detectors, buried deep underground to escape interference, kept coming up short, catching barely a third of the neutrinos their calculations said should be arriving from the sun. This wasn't just a minor discrepancy. It was a glaring hole in our understanding of both particle physics and stellar mechanics. Either we were wrong about how stars work, or we'd fundamentally misunderstood neutrinos themselves. The breakthrough came when researchers realized neutrinos weren't missing, they were shape-shifting. Imagine mailing 100 letters only to have 67 of them mysteriously change color en route. That's essentially what was happening as solar neutrinos raced toward Earth. 3 distinct types, or flavors, exist: electron, muon, and tau neutrinos, and they can spontaneously morph between these identities mid-flight through a quantum phenomenon called oscillation. Early detectors could only spot electron neutrinos, completely blind to the others. The moment scientists built instruments sensitive to all 3 flavors, the numbers matched perfectly. The sun had been sending its full neutrino output all along, we just hadn't been listening on all channels. This discovery didn't just solve a solar puzzle, it shattered a foundational assumption in physics. Neutrinos were long thought to be massless like photons, but oscillation requires mass. Without it, the flavors couldn't switch. That tiny bit of heft, less than a millionth of an electron's mass, forced scientists to revise the standard model of particle physics, our most complete theory of matter. It's astounding that something so slight could upend decades of established science, all because the sun's neutrinos refused to behave as expected. What's even wilder is how this solar neutrino saga revealed the star's inner workings with unprecedented clarity. These particles escaped the sun's core just 8 minutes after being born, while photons, the particles of sunlight we see, take tens of thousands of years to zigzag their way to the surface. Neutrinos give us a real-time snapshot of the sun's nuclear furnace, unaffected by the chaotic outer layers. When detectors finally caught all three flavors, it confirmed our models of stellar fusion with extraordinary precision. We're essentially doing solar astronomy by catching ghosts, using particles that barely interact with anything to study an object 93 million miles away. The implications stretch far beyond our solar system. Neutrino oscillation hints at why the universe contains so much more matter than antimatter, a crucial imbalance that allowed galaxies, stars, and ultimately us to exist. These solar ghosts may hold answers to questions we're only beginning to ask. Next time you feel sunlight warming your skin, remember, trillions of neutrinos are passing through you that instant, unchanged since they left the sun's core. They're both messengers and mysteries, reminding us that even the most familiar objects in the sky still have secrets to share. Neutrino oscillations aren't just a quirky behavior, they're a cosmic magic trick that rewrote the rules of physics. Picture a chameleon crossing a desert, shifting colors with every step. Now imagine that chameleon is a subatomic particle, and the desert is the vast emptiness of space. That's essentially what happens when an electron neutrino born in the sun's core transforms into a muon neutrino halfway to Earth, then maybe even flips to a tau neutrino before reaching your fingertip. This isn't science fiction. It's a quantum reality so bizarre that even physicists initially doubted it could be possible. The implications are staggering. For decades, the standard model, the playbook for particle physics, insisted neutrinos were massless like photons zipping through space at light speed. But oscillation shattered that assumption. Here, why? For neutrinos to change flavors mid-flight, they must experience time differently depending on their mass states, a phenomenon that only works if they have mass. Think of it like tuning forks vibrating at slightly different frequencies. The interference between these states causes the oscillation. The numbers are almost laughably small. The heaviest neutrino weighs less than 1/10,000,000th of an electron. Yet that faint whisper of mass forced scientists to tear out entire chapters of their textbooks and start rewriting. What makes this discovery Nobel-worthy isn't just the physics, it's how neutrinos pulled off the ultimate sleight of hand. When Ray Davis's pioneering experiment in the 1960s caught only a third of the expected solar neutrinos, some dismissed it as faulty equipment. But the ghosts were toying with us. Later detectors like Super, with its 50,000-ton water tank, finally spotted the missing neutrinos. They hadn't vanished, they'd simply changed costumes. The moment scientists realized neutrinos could oscillate, it was like finding a hidden door in a room you've lived in for years. This shape-shifting has cosmic consequences. Neutrinos from a supernova don't arrive as the same flavor they were born as, which means detectors must play a guessing game with the universe's most violent explosions. Even more intriguing, oscillation might explain why the universe isn't just empty space. During the Big Bang, matter and antimatter should have annihilated each other perfectly. But neutrinos, with their asymmetrical oscillations, could have tipped the scales slightly toward matter, allowing galaxies, stars, and eventually us to exist. It's a humbling thought. The reason you're here might hinge on a particle so light it barely registers, yet so cunning it can rewrite its own identity while crossing the void. The real kicker, we still don't know exactly how neutrino mass works. Unlike other particles that get their mass from interactions with the field, neutrinos might play by entirely different rules. Some theories suggest they could be their own antiparticles, a property that would make them cosmic contortionists unlike anything else in nature. Others speculate they might be gateways to hidden dimensions or dark matter. Every time we think we've pinned them down, they slip through our fingers again, oscillating not just between flavors, but between the known and the unknown. So next time you hear about neutrino detectors buried in ice or deep underground, remember, they're not just hunting ghosts. They're decoding a universe where particles change identities like spies, where the tiniest masses hold the keys to cosmic history, and where every oscillation whispers secrets about why everything, from the atoms in your hand to the farthest galaxy, exists at all. The mystery isn't just unsolved, it's still unfolding, one shape-shifting particle at a time. When a star reaches the end of its life in a cataclysmic supernova, the first signal isn't the blinding flash of light that paints galaxies. It's a silent scream of neutrinos. These ghostly particles carry away 99% of the explosion's energy, racing ahead of the shockwave at nearly the speed of light. Long before telescopes catch the first glimmer, underground detectors can sense this neutrino pulse, a cosmic heads-up that something extraordinary is about to light up the sky. It's like getting a text message from the universe minutes before the fireworks begin. Supernova 1987A was the game changer. When this star exploded in the large cloud, 168,000 light-years away, neutrinos arrived hours before the visible light. 3 separate detectors in Japan, IMB in Ohio, and in Russia caught 24 of these elusive particles in a single burst. That might not sound like much, but considering most detectors count neutrinos one by one over years, it was like catching a hailstorm in your hands. These neutrinos weren't just messengers, they were forensic evidence, confirming theories about how stars die. The timing matched predictions perfectly. The neutrinos had escaped the collapsing core first, while the visible explosion took longer to punch through the star's outer layers. What makes this early warning system so valuable is just the bragging rights of seeing an explosion coming. Neutrinos give us a direct line to the supernova's engine room, the collapsing core where elements like gold, uranium, and iodine are forged in seconds. By the time light reaches us, it's been scrambled by expanding debris. But neutrinos, they deliver raw data from ground zero, untouched. Modern networks like SNEWS, the Supernova Early Warning System, link detectors worldwide, ready to sound the alarm if another nearby star goes supernova. When it happens, astronomers will have precious extra hours to point every telescope available, from radio dishes to gamma-ray satellites, capturing the event in unprecedented detail. The stakes are higher than you might think. A Milky Way supernova could release enough neutrinos to outshine the sun's entire output in just 10 seconds. That's not hyperbole. Calculations show the human eye might actually perceive a flash from neutrino interactions in its own fluid if one occurred close enough. Thankfully, the odds are low, but the scientific payoff would be immeasurable. A galactic supernova's neutrinos could reveal secrets about how neutron stars and black holes form, or even uncover new physics beyond the standard model. Imagine standing on a hilltop, feeling a breeze before a storm hits. That's what neutrino astronomers do, except their breeze is a handful of particles from a dying star, and the storm is the birth of elements that will someday form new worlds. Every supernova neutrino we catch is a time capsule from one of the universe's most transformative moments, carrying whispers from the edge of oblivion. And with next-generation detectors like Hyper and Dune coming online, we're building ever more sensitive ears to listen. The next cosmic explosion might happen tomorrow or in a century, but when it does, we'll have front-row seats thanks to the ghostliest particles in existence. There's a tantalizing thread running through modern cosmology, connecting two of the universe's greatest mysteries, neutrinos and dark matter. On the surface, they couldn't seem more different. Neutrinos, though ghostly, are at least detectable in our most sensitive experiments, while dark matter remains utterly invisible, revealing itself only through gravitational tugs on galaxies. Yet physicists are increasingly convinced these cosmic phantoms might be distant relatives in the particle family tree, separated by properties we're only beginning to understand. Consider this puzzling fact. Neutrinos make up about 0.1% of the universe's mass, while dark matter accounts for 27%. That's a staggering difference, but here's where things get interesting. Both share one crucial trait: they barely interact with ordinary matter. Dark matter doesn't emit, absorb, or reflect light, just as neutrinos sail through planets unimpeded. This similarity has led scientists down an intriguing path of speculation. If nature created one type of nearly invisible particle, might there be others, perhaps even heavier cousins to neutrinos, that could explain dark matter's gravitational footprint? Enter the hypothetical sterile neutrino, a fourth flavor that wouldn't interact via the weak force like its three known siblings. These phantom particles would feel only gravity, making them perfect dark matter candidates. While ordinary neutrinos oscillate between electron, muon, and tau types, sterile neutrinos could theoretically mix with them in hidden ways, like a secret ingredient in the cosmic recipe. Experiments like the mini-bueni have spotted anomalies in neutrino behavior that some interpret as whispers of this elusive fourth type. The data isn't conclusive yet, but the possibility sends shivers through the physics community. The implications are profound. If sterile neutrinos exist, they could solve multiple cosmic puzzles at once. Their slight mass might explain why galaxies rotate faster than visible matter can account for. Their decay products could be the mysterious X-ray signals detected from distant galaxy clusters. Even more remarkably, sterile neutrinos might have shaped the universe's large-scale structure, those vast cosmic webs of galaxies separated by voids, in ways ordinary matter never could. While normal neutrinos move too fast to clump together effectively, sterile neutrinos could have just the right mass and speed to form the gravitational scaffolding we observe. This isn't just theoretical daydreaming. Deep underground, detectors like the upcoming Underground Neutrino Observatory in China are being fine-tuned to hunt for sterile neutrino signatures. Space telescopes like ESA's Athena are searching skies for X-rays that might betray their presence. Even the cosmic microwave background, the afterglow of the Big Bang, might hold subtle fingerprints of neutrino-dark matter interactions in the universe's first moments. What makes this search so electrifying is the potential for a two-for-one breakthrough. Discovering sterile neutrinos wouldn't just complete the neutrino family, it could crack open the dark matter enigma that's puzzled astronomers since the 1930s. We might be on the verge of realizing that the universe's ghostliest particles are all part of the same shadowy network, quietly orchestrating the cosmos from behind the scenes. Every neutrino detection brings us closer to answering whether these phantoms are lone wanderers or part of a vast, invisible family shaping everything we see and everything we can't. It was the kind of headline that made physicists spill their coffee: neutrinos breaking the ultimate speed limit. In 2011, the Opera experiment in Italy clocked these ghostly particles, arriving 60 nanoseconds faster than light could have traveled the same distance. That's less than a blink, but in physics terms, it was seismic. If true, it meant theory of relativity, the foundation of modern physics, had a crack in its armor. The implications were dizzying: causality violations, time travel paradoxes, an entire rewrite of cosmic rulebooks. Media outlets ran wild with "wrong" headlines, while scientists worldwide scrambled to verify or debunk the claim. The Opera team hadn't rushed to announce their findings. They'd spent months checking and rechecking, baffled by their own data. Their setup was meticulous, firing neutrinos from CERN in Switzerland through 730 kilometers of solid Earth to a detector under Grand Mountain. GPS satellites synchronized clocks at both ends to within nanoseconds. Yet the numbers stubbornly suggested neutrinos were outpacing light by 0.0025%. Even the researchers presenting the data urged caution, knowing full well the scientific grenade they were tossing. What followed was in how science self-corrects. Teams from Japan to the United States attempted to replicate the results, The Icarus experiment using the same neutrino beam found no speed excess. Then came the smoking gun, a loose fiber optic cable in Opera's timing system, introducing just enough delay to skew the measurements. When tightened, the anomaly vanished. The faster-than-light neutrinos were, in fact, obeying after all. But here's the twist. The episode wasn't just an embarrassing blunder. It revealed how neutrino experiments dance on the razor's edge of measurement precision. Tracking particles that interact so rarely requires engineering so precise that a single faulty connection can upend physics. Modern detectors now account for factors you'd never imagine mattering. The gravitational time dilation between mountain and valley, the slight stretching of Earth's crust from ocean tides, even the pressure of passing weather systems on underground cables. The deeper irony, neutrinos do challenge light speed, just not by exceeding it. Because they have vanishingly small mass, they can't quite reach light speed, always lagging infinitesimally behind. Yet they come staggeringly close, so close that from a supernova 160,000 light-years away, neutrinos and light arrive just hours apart after crossing cosmic distances. That near-perfect tie is its own marvel, a testament to how these ghosts thread the needle of physical laws. Perhaps the greatest lesson from the Opera incident is how neutrinos keep us humble. They tempt us with impossible possibilities, only to reveal our own measurement frailties. Every time we think we've pinned them down, they remind us that the universe's quietest particles still have ways to surprise. Even failed experiments push science forward, because in hunting for ghosts, we build better detectors, sharper theories, and a deeper respect for nature's subtleties. The next breakthrough might not overturn relativity, but it could come from the same relentless pursuit of particles that treat the cosmos as their playground. Imagine the universe in its infancy, a seething, chaotic plasma so dense that not even light could travel freely. In this primordial soup, neutrinos outnumbered protons and electrons by over 1 billion to 1, flooding the cosmos in an unimaginable tide. These weren't just any neutrinos, they were relics of creation itself, forged in the first second after the Big Bang when temperatures exceeded 10 trillion degrees. While most particles were still locked in violent collisions, neutrinos decoupled from the maelstrom almost immediately, streaming outward unimpeded. Their escape marked a pivotal moment, the universe's first draft of structure, written in ghostly ink. What's astonishing is how these ancient neutrinos might have sculpted the cosmos we see today. Though each one carries vanishingly little mass, their collective gravity could have subtly warped the distribution of matter in those critical early moments. Think of it like a cosmic game of billiards, where neutrinos, moving at nearly light speed, nudged clumps of hydrogen gas just enough to determine where galaxies would eventually form. Simulations show their influence might explain why galaxy clusters align in vast filaments and voids, that spiderweb pattern stretching across billions of light years. Without neutrinos, the universe might look startlingly different, perhaps smoother, or clumped in ways we wouldn't recognize. Yet detecting these relic neutrinos remains one of cosmology's greatest challenges. They've cooled over 13.8 billion years, now drifting with barely a whisper of energy, so faint that even cutting-edge detectors strain to sense them. It's like trying to hear a single snowflake land in a roaring blizzard, but the payoff would be extraordinary. Unlike the cosmic microwave background, which shows us the universe at 380,000 years old, relic neutrinos carry information from the first second. They're time capsules from an era before atoms, before stars, before even the forces of nature had fully taken shape. The hunt for these cosmic ghosts has led to some of the most delicate experiments ever conceived. Projects like Ptolemy at Princeton aim to trap relic neutrinos using sheets of graphene chilled to near absolute zero, hoping one might, against all odds, interact with a nucleus and leave a trace. Others analyze the cosmic microwave background for subtle distortions caused by neutrino flows in the early universe. Even gravitational wave observatories might indirectly reveal their presence, as neutrino-driven ripples in spacetime could imprint on signals from colliding black holes. What's truly humbling is realizing how much of the universe's history hinges on particles we're only beginning to understand. Those same neutrinos passing through you right now might have guided the birth of the Milky Way or determined whether Earth would one day orbit a star. They're not just passive bystanders to cosmic evolution. They could be the unseen hands that stack the bricks of reality. And if we ever catch one of those primordial ghosts, it won't just be a scientific triumph. It'll be like finding the first brushstroke on the canvas of existence. Black holes aren't just cosmic vacuum cleaners. They're neutrino powerhouses, spewing out these ghostly particles like sparks from a grinding wheel. Picture the event horizon, that point of no return where even light gets swallowed. Just outside it, matter doesn't go quietly. Gas and dust spiral in at nearly light speed, heated to millions of degrees, creating a particle accelerator more powerful than anything we could build on Earth. In this maelstrom, protons collide with such violence that they shatter into pions, which then decay into high-energy neutrinos. Unlike photons, which get trapped or scattered, these neutrinos bolt straight through the chaos, carrying encoded details about the black hole's ferocious appetite. The most extreme neutrino factories in the universe might be supermassive black holes at the hearts of active galaxies. Take blazars, for instance, monstrous black holes shooting jets of plasma directly toward Earth. In 2018, the IceCube detector in Antarctica traced a single high-energy neutrino back to one of these jets 4 billion light-years away. It was a eureka moment, proof that black hole jets aren't just light shows, they're neutrino cannons. These particles pack energies millions of times greater than those from our Sun, accelerated by magnetic fields so intense they defy imagination. Catching one is like intercepting a bullet fired from across the cosmos, with its trajectory pointing straight back to the gun. But black holes don't just emit neutrinos, they also shred them. When two black holes collide, the gravitational waves they produce ripple through spacetime, but there's another signal hidden in the wreckage. As they spiral inward, their accretion disks may fling out neutrinos in predictable patterns, like a lighthouse beam sweeping past Earth. Theoretically, matching neutrino bursts with gravitational wave events could let us triangulate the collision's exact physics: how hot the disks got, how much matter was ejected, even the black hole's spins. We're essentially piecing together cosmic car crashes by studying the debris that escaped. Then there's the spookiest neutrino source of all. Black hole mergers might create ephemeral neutrino fireballs. Simulations suggest that when two black holes merge, the surrounding plasma can become so dense and hot that it briefly traps neutrinos, only to release them in a delayed burst. It's as if the black holes swallow the neutrinos, then cough them back up moments later. Detecting this echo would be like hearing a scream bounce off walls we didn't know existed, a direct probe into warped spacetime itself. What makes these observations revolutionary isn't just the thrill of discovery. Neutrinos from black holes could solve the century-old mystery of where ultra-high-energy cosmic rays come from. These rays, protons with energies 1,000,000 times greater than the Large Hadron Collider, have puzzled astronomers since their discovery. Neutrinos, being neutral, aren't deflected by magnetic fields, so they travel straight from source to detector, finger-pointing back to their origins. If black holes are indeed the cosmic ray accelerators we suspect, their neutrinos will be the smoking gun. The irony is delicious. Black holes, the ultimate light prisons, become visible through particles that refuse to be trapped. Every neutrino detected from these dark behemoths is a crack in their armor, a whisper from the edge of oblivion. With next-generation detectors like KM3T in the Mediterranean and the expanded IceCube Gen 2, We're building nets large enough to catch more of these messengers from the abyss. They might just reveal how black holes shape galaxies, seed the universe with heavy elements, or even, if theories hold, leak clues about what lies beyond the event horizon. The universe's darkest monsters are talking. We're finally learning to listen. What if the key to unlocking parallel universes has been streaming through your body this whole time? Neutrinos, those ghostly particles we've chased through ice and rock, might be more than cosmic messengers. Some physicists suspect they could be our first tangible link to hidden dimensions or alternate realities. It sounds like science fiction, but the math hints at something extraordinary. These particles already defy expectations by shape-shifting between flavors and barely interacting with matter. What if that's because they're not just passing through our universe, but brushing against others we can't see? The idea stems from string theory, which proposes extra dimensions curled up so tightly they're invisible to us. Neutrinos, with their ethereal nature, might be the only particles sensitive enough to leak into these hidden layers. Imagine blowing smoke rings that occasionally dip below the surface of water. The rings distort slightly as they interact with another medium. Similarly, neutrinos oscillating between flavors could be flickering in and out of unseen dimensions, their mass and behavior subtly altered by realms beyond our perception. Experiments like Minus and Bay have detected anomalies in neutrino oscillation patterns that don't fit standard models. While most scientists attribute these to measurement errors or incomplete physics, a daring few wonder, could the discrepancies be fingerprints of interference? Even wilder is the notion that some neutrinos might not belong to our universe at all. If parallel worlds exist, their versions of stars and black holes would produce their own neutrinos. Occasionally, one might tunnel through the cosmic barrier, like a letter slipped under a door, bringing traces of a reality where physics operates differently. Detectors like IceCube occasionally spot ultra-high-energy neutrinos with no obvious source. Could these be refugees from other dimensions, carrying encoded tales of alien physics? The implications would rewrite science itself. Confirming multiverse neutrinos wouldn't just add a chapter to textbooks, it would burn them down and start fresh. Suddenly, phenomena like dark matter or quantum entanglement might look like side effects of a deeper, multidimensional reality. Critics argue it's premature to make such leaps when mundane explanations exist. But history shows science often advances by chasing ghosts, from radio waves to black holes, that were once dismissed as fantasy. Whether neutrinos open a portal to the multiverse or not, their very strangeness keeps pushing us toward uncomfortable questions. Why does our universe have exactly 3 neutrino flavors? Why do they have mass at all? Each anomaly is a crack in the door, inviting us to peer through. Next-generation experiments like Dune and Hyper will hunt for these cracks with unprecedented precision. If they find even a hint of multidimensional neutrinos, it would be like discovering the first ripple from a shore we never knew existed. Until then, every neutrino detection carries a whisper of possibility, that the universe's shyest particles might be its boldest guides, leading us toward truths we're only beginning to imagine. Neutrinos don't just bend the rules of quantum mechanics, they twist them into knots. At the subatomic level, these ghost particles pull off a magic trick that would make Cat dizzy. They exist as both particles and waves simultaneously, morphing between states in ways that challenge our deepest understandings of reality. Picture a chameleon that doesn't just change colors but flickers between being a lizard, a leaf, and a beam of light, all while vanishing through solid walls. That's the quantum ballet neutrinos perform every nanosecond across the universe, and it's forcing physicists to rethink the very fabric of the standard model. The heart of this quantum conundrum lies in neutrino oscillations, the phenomenon where these particles spontaneously switch flavors mid-flight. Here's where things get truly bizarre. This metamorphosis can only happen if neutrinos are experiencing quantum interference between their mass states, meaning different versions of the same particle are essentially out of phase with each other. It's like a musical chord where each note is playing at a slightly different speed, creating beats that transform the sound. For neutrinos, those beats manifest as changing identities. An electron neutrino leaving the Sun might arrive at Earth as a tau neutrino, having essentially danced through multiple quantum realities along the way. Scientists are now harnessing this quantum weirdness as a tool through neutrino interferometry, a technique so precise it makes regular quantum experiments look blunt by comparison. By firing controlled neutrino beams through miles of bedrock and measuring how their wave patterns interfere, researchers can probe questions that stump traditional particle colliders. The Japanese T2K experiment, for instance, shoots neutrinos 295 kilometers across Japan to study these interference patterns, hunting for discrepancies that might reveal cracks in the standard model. Already, they've found hints that neutrinos and antineutrinos oscillate at different rates, a possible clue to why the universe favors matter over antimatter. What makes neutrinos such potent quantum probes is their sensitivity to effects other particles ignore. Some theories suggest their oscillations might be influenced by dark matter interactions or even spacetime fluctuations at microscopic scales. There's tantalizing, though controversial, data from experiments like Mini-BUNI-AT, where neutrino interactions show anomalies that could point to sterile neutrinos, hypothetical particles that only interact via gravity, potentially bridging quantum physics and general relativity. The implications ripple far beyond particle physics. If neutrinos can help unify quantum mechanics with gravity, they might illuminate black hole singularities or the first moments after the Big Bang. Their quantum behavior could even hold keys to quantum computing, with proposals to use neutrino-like oscillations as qubits in unimaginably powerful processors. Every time we think we've pinned down their rules, they reveal another layer of mystery, like a cosmic matryoshka doll where each opened layer shows a stranger truth beneath. As detectors grow more sophisticated, we're not just observing neutrinos, we're learning to speak their quantum language. Projects like the Deep Underground Neutrino Experiment will soon track oscillations with unprecedented precision, potentially uncovering whether neutrinos violate charge parity symmetry in ways that explain the universe's matter dominance. Others hunt for the faintest quantum imprints left by cosmic relic neutrinos from the Big Bang. Each measurement is like tuning a radio to a new frequency, slowly clarifying a transmission that's been streaming since the dawn of time. The most humbling realization, neutrinos may be showing us that quantum mechanics isn't the final frontier, just the doorway. Their relentless weirdness suggests our current theories are like a flashlight beam trying to illuminate a cavern. We're seeing outlines, but the full dimensions remain hidden. Whether they're gateways to extra dimensions, dark matter messengers, or something even stranger, one thing is clear. The universe's shyest particles are also its most subversive teachers, rewriting the rules one ghostly interaction at a time. Deep beneath the Antarctic ice, where temperatures plunge to -40 degrees and sunlight never reaches, lies one of humanity's most ambitious ghost hunting experiments. The IceCube Neutrino Observatory isn't just a detector, it's a frozen cathedral of science, its sensors embedded in a cubic kilometer of pristine ice like diamonds scattered through a cosmic treasure chest. This icy labyrinth turns Earth's southernmost continent into a colossal neutrino telescope, using the planet itself as a filter to screen out everything but the universe's most elusive particles. What makes IceCube extraordinary isn't just its scale. Over 5,000 basketball-sized optical sensors dangling from 86 vertical strings beneath the ice. But what it catches? Most neutrino detectors measure relatively tame particles from our sun or atmosphere. IceCube hunts the cosmic extremophiles, neutrinos packing energies so fierce they make particles from the Large Hadron Collider look sluggish by comparison. These intergalactic bullets originate in nature's most violent arenas, colliding black holes, erupting quasars, or perhaps even dark matter annihilation. When one of these high-energy phantoms finally interacts with an ice molecule after crossing billions of light years, it creates a subatomic shockwave that briefly turns the ice blue with radiation. That fleeting glow, captured by IceCube's sensors, is our only clue to deciphering the particle's cosmic autobiography. The real magic happens when scientists trace these neutrinos back to their birthplaces. In 2017, IceCube spotted a neutrino with energy exceeding 200, about 40 times more powerful than protons circling the LHC. By cross-referencing its arrival direction with telescope data, researchers traced it to a blazar 4 billion light-years away, a supermassive black hole spearing the cosmos with jets of plasma. It was like finding a single fingerprint at a crime scene and realizing it belonged to a giant. This marked the dawn of neutrino astronomy, using ghost particles as cosmic signposts to locate the universe's most energetic phenomena. Yet for all its achievements, IceCube is essentially playing pin the tail on the donkey with the cosmos. Neutrinos arrive with directional uncertainty of about 1 degree, equivalent to pointing at the moon and saying somewhere in that general area. Future upgrades like IceCube Gen 2 aim to shrink that margin tenfold by expanding the detector array, effectively giving neutrino astronomy glasses to see finer details. Combined with gravitational wave detectors and gamma-ray telescopes, this could create a multi-messenger network capable of triangulating cosmic catastrophes with unprecedented precision. The most poetic part, IceCube's frozen medium isn't just practical, it's poetic justice. Neutrinos spend eons traveling through space largely undisturbed, only to be caught in the one substance transparent enough for their faint signals yet dense enough to occasionally stop them: ancient Antarctic ice. Every detection is a cosmic coincidence of staggering improbability. A particle from a distant catastrophe meeting Earth at just the right place and time, its story frozen in ice until curious humans thought to listen. And with each new ghost captured, we're reminded that some of the universe's loudest stories are told in whispers. Every nuclear reactor on Earth is secretly a neutrino factory, churning out trillions of these ghostly particles every second. While stars and supernovas dominate the cosmic neutrino landscape, our own fission reactors provide something invaluable: a controlled, predictable source right here on our planet. When uranium atoms split inside reactor cores, the resulting nuclear ballet doesn't just produce energy. It spawns electron antineutrinos as fleeting byproducts, each carrying a precise fingerprint of the radioactive decay that birthed it. These man-made ghosts have become unlikely allies in science's quest to unravel neutrino mysteries, offering a unique testing ground buried not under Antarctic ice, but within our energy infrastructure. The magic lies in their consistency. Unlike cosmic neutrinos that arrive with unknown histories, reactor neutrinos emerge with energies and fluxes that engineers can calculate down to the decimal. This predictability turns power plants into natural laboratories. Experiments like Bay in China and Double in France position detectors near reactors to catch these antineutrinos, measuring how many disappear as they oscillate into undetectable flavors. The results have sharpened our estimates of neutrino mixing angles, key parameters in the oscillation puzzle, with precision that cosmic sources can't match. It's ironic. We harness the atom's power for electricity, and in return, it hands us clues about fundamental physics. But reactor neutrinos aren't just scientific tools, they're nuclear watchdogs. Every fission reaction produces a telltale neutrino, flux proportional to the reactor's power output. By placing detectors near known reactors, scientists can verify non-proliferation agreements remotely, as any unexplained drop in neutrinos might suggest fuel diversion. The Watchman project, for instance, aims to deploy water-based detectors hundreds of kilometers from reactors, using neutrino signatures as tamper-proof monitoring. Unlike satellite imagery or inspections, you can't hide neutrinos behind concrete walls or lead shielding. They'll whistle through anything, carrying truth from the core. Perhaps most astonishing is how reactor experiments keep stumbling into surprises. In the early 21st century, multiple detectors found fewer antineutrinos than predicted at specific energy ranges, a discrepancy called the reactor antineutrino anomaly. Some speculated it might hint at sterile neutrinos, while others blamed incomplete nuclear data. The debate still simmers, proving even our engineered neutrino sources harbor mysteries. Modern efforts like Prospect at Oak Ridge National Laboratory use highly enriched uranium to produce cleaner neutrino beams, eliminating uncertainties from mixed reactor fuels. The takeaway is profound. Humanity has unwittingly been conducting neutrino physics for decades, long before we understood their significance. Those cooling towers silhouetted against sunset skies aren't just powering cities, they're casting ghostly shadows of subatomic particles, a hidden dimension to our technological footprint. Next-generation reactors, like molten salt designs, could offer even richer neutrino harvests, their unique fission spectra opening new measurement possibilities. From keeping nuclear peace to refining quantum models, these man-made ghosts remind us that the universe's shyest particles are everywhere, even in the glow of our own creations. The search for extraterrestrial intelligence has always been a game of guessing how an alien civilization might announce its presence. For decades, we've scanned the skies for radio waves, the cosmic equivalent of shouting into the void. But what if advanced societies have moved beyond primitive radio, mastering a far more subtle language? Imagine a communication system built not on electromagnetic waves but on neutrinos, particles that slice through planets, stars, and dust clouds without distortion. It's a radical idea, but one that's gaining traction among scientists at the forefront of SETI. Neutrino-based messaging would solve some of the universe's greatest communication headaches. Radio signals weaken over distance, scattering into noise. Light gets absorbed by interstellar gas or bent by gravitational lenses. But a neutrino beam, it could cross billions of light years virtually unchanged, carrying a pristine signal from a distant transmitter. An advanced civilization might see neutrinos as the ultimate cosmic fiber optics, delivering data through galactic walls with near-perfect fidelity. Theoretically, a single high-energy neutrino pulse could outshine all the stars in its path, creating a beacon detectable across the observable universe. This isn't just speculation. Projects like New SETI are already adapting neutrino detectors to listen for artificial patterns. Traditional SETI dishes scan specific radio frequencies. Neutrino hunters look for anomalous bursts, sequences too precise to be natural. Imagine detecting a series of neutrinos arriving in prime number intervals or encoding mathematical constants. That wouldn't just be evidence of life, it would be proof of intelligence deliberately reaching out. The challenge, of course, is separating such signals from the cacophony of natural neutrino sources. Supernovae, black holes, and even Earth's own reactors create background chatter. But as detectors grow more sensitive, the odds improve. The real intrigue lies in what neutrino messages might contain. Unlike radio broadcasts, which could carry spoken language or music, neutrinos might transmit something far richer: quantum-encoded data, multidimensional blueprints, or even compressed simulations of alien worlds. Decoding such a signal would be like finding a USB drive in the ruins of an ancient civilization, if the USB were made of pure energy and required rewriting the laws of physics to read. Some theorists suggest that civilizations advanced enough to harness neutrinos might use them not just for communication, but as a form of cosmic archaeology, sending probes backward through time to study the early universe. Critics argue that neutrino communication remains a long shot, requiring energies beyond any known technology. But that's exactly the point. Humanity's own technological leaps seemed impossible until they weren't. A century ago, radio waves were laboratory curiosities. Today, they blanket the globe. If other civilizations are millions of years ahead, their mastery of neutrinos might be as routine as our use of microwaves. The search for alien neutrinos forces us to confront a humbling question. What if we've been listening for whispers in a room where everyone else is using sign language? As neutrino astronomy matures, we may discover that the universe's greatest conversations have been happening right under our noses, or rather, straight through them, all along. Whether we ever intercept such a message or not, the pursuit reshapes how we imagine intelligence itself, reminding us that the cosmos might be speaking in a tongue we're only beginning to decipher. Here's a cosmic puzzle that sounds simple but could rewrite our understanding of the universe. When neutrinos shake off their massless reputation and finally admit they have weight, which of the three flavors tips the scales as the heaviest? This isn't just academic nitpicking. It's the neutrino mass hierarchy problem, a mystery so fundamental that cracking it might explain why anything exists at all. Picture a set of quantum scales where the order of neutrino masses, whether electron, muon, or tau neutrinos sit at the top, holds clues to one of physics' biggest head-scratchers. Why the cosmos didn't annihilate itself in a perfect matter-antimatter fireball after the Big Bang. The stakes are sky-high because neutrinos don't play fair. While electrons neatly stack from to heaviest, neutrinos oscillate between flavors so unpredictably that their mass order remains scrambled. Two competing scenarios dominate the debate: the normal hierarchy, where the electron neutrino is the mirroring other particle families, and the inverted hierarchy, which flips the script, placing it in the middle like a cosmic oddball. The difference might seem trivial, but it's anything but. If the inverted hierarchy proves true, it would upend our assumptions about how particles organize themselves, hinting at entirely new physics beyond the standard model. Experiments are closing in from all angles. Japan's T2K fires neutrino beams through Earth to study how often muon neutrinos transform into electron types, a rate that subtly depends on the mass hierarchy. Meanwhile, the deep underground neutrino experiment in the United States will shoot particles 800 miles from to South Dakota, watching for telltale oscillation patterns in unprecedented detail. Even nature's own neutrino factories, supernovae, could weigh in. When a star explodes, the sequence in which different neutrino flavors arrive at Earth carries encrypted hints about their mass order, like a cosmic Morse code. The hierarchy's implications stretch far beyond particle physics. If neutrinos helped tip the early universe toward matter dominance, their mass order could determine whether that process was inevitable or a quantum fluke. Certain hierarchy arrangements would make neutrinos more likely candidates for dark matter components or reveal connections to grand unified theories. It's as if we've found a single loose thread in the fabric of reality, and pulling it might unravel secrets from the quark scale to the cosmic web. What makes this search so thrilling is its sheer audacity. We're measuring differences tinier than a snowflake's weight in a hurricane, all to answer a question that shapes existence itself. Every flicker of data from these experiments isn't just filling a textbook. It's deciding whether our universe's matter-rich fate was written into neutrinos from the beginning. The detectors humming away underground aren't just machines. They're time machines, decoding decisions made in the first fractions of a second after creation. And when they finally catch that elusive hierarchy, it won't just be a footnote in physics history. It'll be the moment we glimpse the hidden rules that let something, stars, planets, us, emerge from nothingness. Neutrinos might hold the key to one of physics' most tantalizing thought experiments, time travel. On the surface, the idea sounds ripped from science fiction, but when you examine how these particles flirt with the edges of known physics, the possibility becomes strangely plausible. At the heart of this theory lies a peculiar quirk in the equations of quantum mechanics. Certain solutions suggest neutrinos could behave as if they're moving backward through time. It's not that they're literally reversing time like a clock running backward. Rather, their quantum properties might mimic the effects of, making them appear to influence events before they've technically occurred. This bizarre notion stems from how neutrinos interact with the fabric of spacetime. Unlike most particles, which follow a clear, forward-moving timeline, neutrinos seem to dance along the razor's edge of causality. Some interpretations of quantum field theory propose that antineutrinos, the antimatter counterparts to neutrinos, could mathematically represent neutrinos traveling backward in time. It's as if the universe keeps two sets of books, one where a neutrino moves forward and another where its antineutrino twin retraces its steps. This symmetry, known as the CPT theorem, suggests that reversing a particle's charge, parity, and time should leave the laws of physics unchanged. For neutrinos, which barely acknowledge these properties to begin with, the lines between past and future blur in ways that defy intuition. The implications are staggering. If neutrinos can indeed skirt the usual rules of cause and effect, they might carry information from the future to the past, or reveal hidden connections between events separated by time. Imagine a detector catching a neutrino from a supernova before telescopes see the explosion, not because the neutrino traveled faster than light, but because it effectively arrived before the light left. Such a scenario would force us to rethink everything from quantum computing to the origins of the universe. Experiments like MINUS and OPERA have already glimpsed anomalies in neutrino timing that, while likely due to measurement errors, sparked brief speculation about time-bending behavior. Of course, mainstream physics remains skeptical. Most physicists attribute these oddities to the quirks of neutrino oscillations or detector limitations rather than temporal trickery. Yet the very fact that such wild ideas persist in credible circles speaks to how little we truly understand about these particles. Neutrinos have already shattered assumptions about mass, identity, and cosmic influence. Why not time itself? Even if the time travel hypothesis never pans out, the pursuit forces us to confront deeper questions about reality's structure. Are the laws of causality as rigid as we think, or is there wiggle room at the quantum level? For now, the idea remains a playground for theorists, a what-if scenario that stretches imagination without breaking scientific rigor. But if history has taught us anything, it's that neutrinos specialize in the unexpected. Whether they're whispering secrets from parallel dimensions or simply revealing gaps in our models, one thing is certain: the universe's shyest particles still have surprises up their sleeves. And if those surprises include even a hint of temporal mischief, the ghost particle conspiracy might just rewrite time itself. Neutrinos have slipped from physics labs into our collective imagination, becoming unlikely stars of science fiction and conspiracy lore. Arthur C. 2010, Odyssey 2, envisioned an alien civilization using neutrino beams to communicate across light years, a concept that wasn't pure fantasy. Real-world physicists have since proposed similar ideas for interstellar messaging. Then there's the Flash, where a neutrino bomb threatens Central City, tapping into the public's awe of these particles' barely harnessed power. Hollywood loves neutrinos precisely because they're both real and mysterious enough to fuel wild narratives, ghostly yet tangible, invisible yet omnipresent. But where sci-fi explores, conspiracy theories distort. Online forums buzz with claims that governments weaponize neutrinos for weather control or mind manipulation. Some allege secret projects like HAARP in Alaska beam neutrino pulses to trigger earthquakes, despite physicists pointing out the energy required would dwarf humanity's total power output. Others insist neutrino detectors are really surveillance tools, spying through walls and mountains. These myths persist because neutrinos' actual physics, penetrating anywhere, rarely interacting, sounds like something from a spy thriller. The irony: real neutrino science is stranger than any conspiracy. While theorists spin tales of shadowy control, actual researchers strain to catch a handful of particles from dying stars, using instruments buried deep underground to filter out cosmic noise. The cultural obsession reveals something profound. Neutrinos bridge the gap between hard science and human wonder. They're one of the few quantum-scale phenomena that feel almost magical, particles that defy barriers, shift identities, and might hold universe-shaping secrets. When a TV show like Stranger Things references neutrinos to explain parallel dimensions, or a video game like Mass Effect uses them as plot devices, they're tapping into that same sense of mystery that drives physicists to build ice-bound telescopes and mineshaft detectors. Perhaps the most telling fictional portrayal came in Star Trek: The Next Generation, where LaForge casually mentions neutrino emissions while troubleshooting the Enterprise's engines. It's a blink-and-you'll-miss-it moment, but it captures how neutrinos have permeated pop culture, not just as plot twists, but as background texture for futuristic realism. That's the neutrino's true cultural victory, evolving from an obscure physics footnote to a shorthand for cutting-edge science, whether accurately used or wildly misappropriated. The line between fact and fiction blurs because neutrinos themselves resist easy categorization. They're messengers from cosmic violence we can't witness, keys to puzzles we haven't fully framed. When conspiracy theorists claim hidden powers or screenwriters spin interstellar tales, they're riffing on the same enigma that keeps physicists awake at night: the difference. Scientists chase neutrinos with math and steel, while storytellers harness their mystique to remind us that the universe is far weirder and more wonderful than we dare imagine. Neutrinos aren't just cosmic messengers. They might be the ultimate Earth detectives, uncovering secrets buried deep beneath our feet. Picture this: while most of us worry about volcanic eruptions only when ash clouds darken the sky, scientists are exploring whether ghost particles could give us an early warning. It sounds like science fiction, but here's the reality. When magma churns beneath a volcano, radioactive elements like uranium and thorium decay, releasing antineutrinos in predictable patterns. These particles zip straight through miles of rock, carrying a live feed of the volcano's activity. Catching them could reveal pressure building underground weeks or even months before the first tremors, like getting a text from the Earth's molten heart saying, "Heads up, things are getting hot down here." The concept isn't just theoretical. Japan's land detector, originally built to study solar neutrinos, accidentally became a geologic tool when it spotted antineutrinos from natural radioactive decay in Earth's crust and mantle. Suddenly, physicists realized their neutrino detectors were also underground X-ray machines, imaging our planet's interior in ways seismic waves never could. Traditional volcano monitoring relies on surface measurements, gas emissions, ground deformation, earthquake swarms, all indirect clues. Neutrinos, by contrast, offer a direct line to the source, untouched by the distortions of rock layers or magma viscosity. Imagine the difference between diagnosing an engine problem by listening to the hood versus having a real-time scan of every moving piston. But volcanoes are just the start. Neutrino detectors could revolutionize how we track nuclear reactors, not just for non-proliferation, but for climate science. Hidden nuclear tests or unreported reactor activity leave neutrino fingerprints, and unlike satellite imagery, these signals can't be masked. More intriguingly, geothermal energy, a clean but underutilized resource, might be mapped in unprecedented detail. Earth's internal heat drives everything from ocean currents to long-term climate shifts, yet we've barely scratched the surface of understanding its distribution. Future neutrino observatories could create 3D heat maps of the mantle, revealing how energy flows between continents like hidden weather systems. The challenge: sensitivity. Current detectors like Super would need upgrades to pinpoint individual volcanic sources, but next-gen projects like Hyper aim to do just that. Picture arrays of sensors encircling known volcanic hotspots, forming a neutrino early warning network. Combine that with AI analyzing real-time data, and suddenly we're not just reacting to eruptions, we're anticipating them. The same tech might even monitor carbon sequestration sites, ensuring stored CO2 stays trapped by detecting telltale neutrino signatures of underground chemical reactions. What makes this approach so elegant is its simplicity. Neutrinos don't require invasive drilling or guesswork. They stream through everything, delivering unfiltered truths about our planet's hidden machinery. While we've spent centuries studying Earth from the outside, these ghost particles offer a backstage pass to the forces shaping our climate, our geology, even our safety. The same detectors hunting supernovae and dark matter might one day sit silently beneath cities, not just listening to the stars, but keeping watch on the restless ground beneath our feet. The next generation of neutrino detectors isn't just an upgrade, it's a quantum leap into unexplored realms of physics. Hyper, currently under construction in Japan, will be the world's largest water detector, holding 260,000 tons of water, 5 times the volume of its predecessor. This isn't mere scale for bragging rights. Every additional ton increases the odds of catching neutrinos from supernovae in distant galaxies, potentially giving us a front-row seat to stellar deaths across the observable universe. The detector's improved light sensors can spot individual photons with nanosecond precision, allowing it to reconstruct neutrino interactions in 3 dimensions like a subatomic sonar. What makes Hyper-K truly revolutionary is its dual-purpose design. It won't just wait for cosmic neutrinos, but also precisely measure man-made beams shot from 300 kilometers away, creating the most detailed oscillation maps ever made. Meanwhile, across the Pacific, the deep underground neutrino experiment DUNE is taking a radically different approach. Nestled in a former gold mine in South Dakota, DUNE will fill 4 colossal tanks with 70,000 tons of liquid argon kept at -186 degrees Celsius. When a neutrino interacts in this frigid bath, it knocks electrons loose that drift through an electric field, creating telltale trails that detectors can reconstruct with millimeter precision. This technology offers something water detectors can't: the ability to distinguish between neutrino and antineutrino interactions with near-perfect clarity. That distinction is crucial for hunting CP violation, a subtle asymmetry between matter and antimatter that might explain why our universe isn't just empty space. DUNE's long baseline design beams neutrinos 800 miles from in Illinois, giving them enough distance to oscillate multiple times like a quantum slalom course. The scientific quarry these detectors pursue reads like a physics. First on the agenda, determining whether neutrinos violate charge parity symmetry, a phenomenon where neutrinos and antineutrinos oscillate at different rates. If confirmed, this could finally explain why the post-Big Bang universe favored matter over antimatter. Next comes the neutrino mass hierarchy puzzle, figuring out which flavor is the heaviest, a detail that might reveal whether neutrinos get their mass from the field or some exotic new physics. Both experiments will also serve as supernova early warning systems, with Hyper-K capable of detecting 5,000 neutrinos from a single galactic core collapse, enough to reconstruct the star's death throes in slow motion. Most tantalizing is the hunt for relic neutrinos from the Big Bang. These ancient particles, cooled to near absolute zero over 13.8 billion years, would be the oldest identifiable matter in existence. Catching even one would be like finding a fossilized whisper from creation's first second. Dune's liquid argon and Hyper-K's water each offer unique advantages in this cosmic archaeology. Argon's precise tracking might spot low-energy recoils, while water's sheer volume increases the odds of a rare interaction. Success would open an entirely new window into the universe's infancy, before protons formed or light could travel freely. The scale of these projects boggles the mind. Dune's excavation removed 800,000 tons of rock, equivalent to digging 2 Panama canals, while Hyper-K's water purification system must filter out contaminants at parts per trillion levels, making it cleaner than laboratory-grade solvents. The international collaboration behind them spans dozens of countries, with contributions ranging from Argentina's cryogenic expertise to Russia's photodetector technology. This isn't just big science, it's humanity's collective microscope turned toward the quantum frontier. What makes this era unique is how these detectors complement each other rather than compete. Hyper-K excels at catching high-energy neutrinos from astrophysical cataclysms, while Dune's precision tracking unravels subtle quantum effects. Together, they form a neutrino observatory network spanning the globe and probing every energy scale. The data they'll collect could settle century-old debates about matter's origins while uncovering phenomena we haven't even dreamed of yet. When these detectors switch on later this decade, we won't just be upgrading our tools. We'll be giving the universe new ways to speak to us, in a language of ghost particles we're finally learning to hear. If you could rewind the universe like a film strip, peeling back 13.8 billion years to its fiery opening scene, you'd find a moment so dense and hot that even atoms couldn't exist. In that primordial inferno, less than 1 second after the Big Bang, the first neutrinos shook free from the cosmic plasma, flooding space with trillions upon trillions of ghostly particles. Today, that ancient tide still washes through the cosmos, a relic neutrino background so faint it makes the cosmic microwave radiation seem deafening by comparison. These aren't just any neutrinos. They're time travelers from the universe's infancy, carrying whispers of a time before protons, before light could travel freely, before anything recognizable as matter had taken shape. Detecting these cosmic fossils would be like finding a perfectly preserved dinosaur feather in your backyard, except the feather is lighter than a single photon, and your backyard is the entire observable universe. The challenge is staggering. While the cosmic microwave background paints a picture of the universe at 380,000 years old, relic neutrinos would snap a Polaroid from its first full second. The difference is like comparing a toddler's photo to an ultrasound. But here's the catch. Over billions of years, the expansion of space has stretched these neutrinos' wavelengths to the point where their energy is less than 1,000th of n. They drift through you now with less kick than a snowflake landing on your skin, their signals drowned out by the roar of modern neutrinos from the sun, reactors, and cosmic rays. Scientists aren't giving up. The Ptolemy project at Princeton is pioneering a radical approach, using graphene sheets chilled to near absolute zero to trap these ultra-low-energy ghosts. The idea hinges on a wild quantum trick. When a relic neutrino interacts with a nucleus, it should produce an almost imperceptible recoil. By stacking ultra-thin graphene layers, each just 1 atom thick, researchers aim to amplify that tiny bump into something measurable. It's like trying to hear a pin drop in a hurricane by inventing a microphone sensitive enough to catch the sound of air molecules brushing against the pin. Other proposals are even more audacious, like hunting for the faint imprints relic neutrinos left on the cosmic microwave background. Subtle distortions in that afterglow that might reveal how these particles subtly tugged at the infant universe's fabric. Why go to such extremes? Because relic neutrinos could answer questions that keep cosmologists awake at night. Their energy distribution would reveal exactly when they decoupled from other matter, a critical timestamp in cosmic evolution. Their abundance might explain why the universe's expansion rate doesn't quite match predictions. Some theories even suggest these ancient particles could interact with dark matter in ways that would rewrite our understanding of both. And if, against all odds, they carry even a hint of asymmetry between matter and antimatter, it might finally solve the mystery of why we exist at all. The hunt for relic neutrinos is more than a technical challenge. It's a philosophical pilgrimage to the edge of knowable time. Every other particle we study has been reshaped by billions of years of cosmic history, but these ghosts are unchanged witnesses to creation's first breath. If we ever catch one, it won't just be a scientific triumph. It'll be like holding a piece of the Big Bang itself, a fragment of the moment when everything, from the stars to your fingertips, first flickered into being. Until then, they remain the universe's oldest secret, streaming through our detectors, our planet, and even our bodies, untouched since the dawn of time. The standard model of particle physics is humanity's most precise blueprint of reality, a masterpiece that's predicted everything from the boson to quantum entanglement with jaw-dropping accuracy. Yet for all its triumphs, there's one glaring hole in its elegant equations, and it's shaped like a neutrino. These ghostly particles refuse to fit neatly into the model's framework, not because they don't belong, but because they're holding secrets that could crack the whole thing wide open. The puzzle: mass every other particle in the standard model gets its heft from interactions with the field, like wading through cosmic molasses that slows them just enough to register on the scale. But neutrinos, they're the cosmic minimalists, weighing in at less than a millionth of an electron, yet somehow avoiding the mechanism entirely. It's as if they've found it to existence, and physicists are desperate to pick the lock. This isn't just academic nitpicking, it's a potential gateway to realms beyond the standard model. One leading theory suggests neutrinos might be particles, a bizarre class of matter that are their own antiparticles. If true, it would mean every neutrino is simultaneously itself and its own mirror image, like a quantum-scale strip where matter and antimatter blur into one. Experiments like the GERDA project in Italy are hunting for this smoking gun by searching for an ultra-rare nuclear decay called double beta decay, where neutrinos effectively vanish into their own antimatter versions. Spotting this would rewrite physics overnight, proving that neutrinos operate by rules we've never imagined. Then there's the supersymmetry angle. Many theorists believe every known particle has a heavier, superpartner waiting to be discovered, a symmetry that could neatly explain dark matter and unify nature's forces. Neutrinos, with their unexplained lightness, might be the first whisper of this hidden family. Their tiny masses could arise from interactions with these hypothetical superpartners, like cosmic seesaws where the neutrino's lightness balances out some unseen heavy particle. It's a mathematical dance that feels almost too elegant to be wrong, yet so far, colliders like the LHC have found no trace of these superpartners. Neutrinos keep teasing us, their behavior hints at new physics, but the full picture stays frustratingly out of focus. Perhaps the wildest possibility is that neutrinos are tapping into extra dimensions. String theory proposes that our universe has more than the familiar 3 dimensions of space, with the rest curled up too tightly to perceive. Neutrinos, barely interacting with our world, might be the only particles sensitive enough to leak into these hidden layers. This could explain their vanishingly small masses. What we perceive as a featherweight particle might actually be a heavyweight vibrating across multiple dimensions, its full mass diluted through realities we can't see. Experiments like MINUS and NA have spotted oddities in neutrino oscillation patterns that don't quite fit predictions, fueling speculation that extra-dimensional tweaks might be at play. The stakes couldn't be higher. Cracking the neutrino mass mystery might do more than patch the standard model. It could reveal an entirely new physics playing field. Quantum mechanics and general relativity, the twin pillars of modern physics, remain stubbornly incompatible at their cores. But neutrinos, threading the needle between the quantum realm and cosmic scales, might carry the first clues to their reconciliation. Every anomaly in their behavior, every unexpected oscillation or energy discrepancy, is like a faint signal from a shore we haven't mapped yet. What makes this search so electrifying is its sheer unpredictability. Neutrinos have already us twice, first by proving they have mass, then by showing they can change identities mid-flight. The next revelation could be equally disruptive, whether it's proof of supersymmetry, evidence of extra dimensions, or something even stranger. As detectors grow more sensitive and theorists refine their models, we're not just chasing particles. We're chasing the possibility that everything we know about the universe is just the tip of an iceberg, with neutrinos as our guides to what lies beneath. The standard model isn't wrong, it's incomplete. And neutrinos, those quietest of cosmic messengers, might be the ones to finish the sentence. Ultra-high-energy cosmic rays have been raining down on Earth for over a century, carrying energies that dwarf anything our most powerful particle accelerators can produce. These subatomic bullets, mostly protons and atomic nuclei, strike our atmosphere with the force of a major league fastball, all packed into a single particle. But here's the cosmic whodunit. Despite decades of hunting, we still don't know what cosmic engines can launch matter to such insane speeds. The leading suspects, active galactic nuclei, gamma-ray bursts, and colliding galaxy clusters, all lack definitive evidence. That's where neutrinos enter the scene as nature's ultimate snitches. When cosmic rays collide with interstellar gas or radiation near their sources, they spawn high-energy neutrinos as telltale byproducts. Unlike the charged cosmic rays that get scrambled by magnetic fields during their journey, neutrinos fly straight as arrows, pointing directly back to their birthplaces. The Pierre Auger Observatory in Argentina embodies this two-pronged detective work. Spread across 3,000 square kilometers of pampas grassland, it's essentially a giant cosmic ray catcher, an array of 1,600 water tanks that detect the particle showers created when cosmic rays hit the atmosphere. But the real genius lies in its hybrid design. Auger also scans the skies for ultraviolet flashes caused by neutrino interactions in the air, creating the world's largest neutrino telescope looking upward instead of down. When a neutrino from a distant blazar or colliding galaxies happens to interact overhead, Auger can triangulate its direction with surprising precision. The dream scenario. Spotting both a cosmic ray air shower and its sibling neutrino arriving from the same patch of sky. A cosmic fingerprint that would finally nail down these mysterious accelerators. What makes this partnership so powerful is how neutrinos compensate for cosmic rays' greatest weakness. Imagine trying to trace a bullet's origin by studying its trajectory after it ricochets off a dozen walls. That's the challenge with cosmic rays, as galactic magnetic fields bend their paths into unrecognizable curves. Neutrinos, being electrically neutral, ignore these fields completely. A single high-energy neutrino detection with a matching cosmic ray could reveal sources hidden behind cosmic dust clouds or lurking in galaxy cores too turbulent for traditional astronomy. IceCube's detection of a neutrino from blazar TXS 506+056 in 2017 gave us a taste of this potential. When astronomers swiveled telescopes toward its origin, they found the blazar flaring in gamma rays, strong circumstantial evidence that such active galaxies might indeed be cosmic ray factories. The Holy Grail would be catching a neutrino from a Greisen event, a theoretical phenomenon where ultra-high-energy cosmic rays interact with the cosmic microwave background, creating neutrino bursts that could help map the universe's large-scale structure. These events would carry energies surpassing 100 millions of times more powerful than anything the LHC produces. Projects like the proposed Giant Radio Array for Neutrino Detection aim to spot these ultra-rare interactions by monitoring radio waves emitted when neutrinos plow through Antarctic ice or lunar soil. Solving this century-old mystery wouldn't just satisfy scientific curiosity, it would rewrite our understanding of nature's ultimate particle accelerators. The energies involved make supernovae look like firecrackers. We're talking processes that can hurl particles with the kinetic energy of a speeding tennis ball, all concentrated into a single proton. Some theories suggest cosmic rays might originate from phenomena we haven't even discovered yet: cosmic strings, decaying dark matter, or collisions in extra dimensions. Neutrinos give us a fighting chance to explore these frontiers, not by building bigger colliders, but by turning the universe itself into our laboratory. Every time a neutrino and cosmic ray arrive hand in hand from the void, it's like receiving a postcard from the universe's most extreme neighborhoods, stamped with an address we're only beginning to decode. The beauty of this neutrino-cosmic ray partnership lies in its complementary nature. Cosmic rays bring the raw power, particles with energies so high they shouldn't survive the journey across intergalactic space. Neutrinos bring the pristine directional information, untouched by magnetic detours. Together, they form a complete investigative toolkit, like combining a witness's testimony with forensic evidence. As next-generation detectors like the Auger Prime upgrade and the Pacific Ocean Neutrino experiment come online, we're not just closing in on an answer. We're pioneering an entirely new way to do astronomy, where invisible particles become our eyes into the cosmos's most violent corners. The solution to this 100-year puzzle might finally be within reach, carried on the wings of ghost particles we've only recently learned to see. Neutrinos might be the universe's most unlikely peacemakers in physics' longest-running feud, the battle to reconcile theory of gravity with the bizarre rules of quantum mechanics. For over a century, these two pillars of modern science have refused to play nice. General relativity paints gravity as the smooth bending of spacetime, while quantum mechanics insists everything is granular, flickering in and out of existence. The result: a theoretical stalemate that's left everyone from Stephen Hawking to today's grad students scratching their heads. But here, where neutrinos waltz in, these shape-shifting phantoms interact so delicately with the universe that they might be the only particles sensitive enough to feel gravity's quantum whispers, without the noise drowning out the signal. Picture spacetime not as a static stage, but as a frothing quantum foam at microscopic scales, a seething mess of virtual particles and wormholes blinking in and out of existence. Most particles are too bulky or too busy interacting with other forces to notice this chaos. Neutrinos, their featherweights dancing on the foam's surface, their oscillations potentially swayed by spacetime's tiniest tremors. At extreme energies, like those near black holes or in the early universe, these effects might amplify just enough to leave fingerprints in neutrino data. It's as if the universe encoded a secret message in the world's shyest particles, waiting for us to develop the right decoder ring. The hunt for these clues is already. When the IceCube detector in Antarctica spotted a handful of ultra-high-energy neutrinos with no obvious source, theorists perked up. Some speculated these outliers might carry traces of quantum gravity effects, perhaps evidence that spacetime has a graininess neutrinos can sense at certain scales. Other experiments, like ANITA, have detected anomalous neutrinos seemingly arriving from angles that defy conventional physics. While most scientists attribute these to measurement errors or exotic astrophysics, a daring few wonder, could they be glimpses of gravity's quantum underbelly, warping neutrino paths in ways never predicted. The real test may come from neutrinos born in cosmic catastrophes. When two neutron stars collide or a black hole shreds a star, the resulting neutrino bursts could serve as stress tests for quantum gravity. Theories like loop quantum gravity or string theory predict subtle delays in neutrino arrival times, fractions of a second over billions of light years, if spacetime isn't perfectly smooth. It's the equivalent of throwing a handful of pebbles into a pond and noticing some ripple slower because the water has hidden texture. Next-generation detectors like IceCube Gen 2 and the Pacific Ocean Neutrino Experiment aim to catch these bursts with precision timing, turning neutrinos into cosmic stopwatches. Even wilder is the possibility that neutrinos could reveal extra dimensions, a key feature of string theory. If gravity leaks into hidden spatial dimensions at small scales, neutrinos oscillating through these realms might gain unexpected mass or change flavors differently than standard models predict. Projects like Dune and Hyper are fine-tuning their oscillation measurements to hunt for these anomalies. A deviation here wouldn't just confirm extra dimensions. It might explain why gravity is so weak compared to other forces, because it's literally diluted across realities we can't see. What makes neutrinos such perfect quantum gravity probes is their quantum weirdness married to cosmic endurance. They're the only particles that can cross the observable universe without getting absorbed or deflected, yet they're also governed by quantum uncertainty, capable of existing in multiple states simultaneously. This dual citizenship in both realms positions them uniquely as emissaries between gravity and quantum physics. Every neutrino detection is like intercepting a letter written in two languages, one we understand and one we're just starting to decipher. The implications are staggering. If neutrinos confirm even a hint of quantum gravity, it would rank among humanity's greatest intellectual leaps, a unification of frameworks that have stood separate since the 1920s. We might finally understand what happens inside black holes, or how the universe emerged from nothingness. Or the data might point somewhere entirely unexpected, revealing that spacetime, like neutrinos themselves, is far stranger than we've dared imagine. One thing's certain, the universe's quietest particles are whispering secrets about its deepest laws. We're finally building the ears to hear them. If the universe played fair, everything we know, stars, planets, even our own bodies, should have vanished in a flash of mutual annihilation moments after the Big Bang. Here, why? Matter and antimatter are perfect mirror images, born in equal amounts during creation. When they meet, they obliterate each other in bursts of pure energy. Yet somehow, against all odds, 1 in every billion matter particles survived. That slim surplus is why galaxies, chemistry, and life itself exist. The question haunting physicists for decades is simple: what tipped the scales? The answer might lie in the universe's most ambivalent particles, neutrinos, and their baffling refusal to follow the rules. At the heart of this mystery is a phenomenon called CP violation, a tiny asymmetry in how particles and their antimatter counterparts behave. The standard model predicts some CP violation, but not nearly enough to explain the cosmic matter surplus. Enter neutrinos. If these shape-shifting ghosts oscillate differently from antineutrinos, changing flavors at slightly different rates, it could amplify that asymmetry to universe-saving levels. Think of it like a coin flip that inexplicably lands heads up 51 times out of 100. Over billions of years in the early universe's particle soup, that 1% bias could have snowballed into the matter-dominated cosmos we inhabit. Experiments like Japan's T2K are hunting for this neutrino bias with painstaking precision. By firing beams of neutrinos and antineutrinos 295 kilometers through Earth to the superdetector, scientists compare how often each type morphs between flavors. Early data shows tantalizing hints of divergence, might oscillate about 5% less frequently than their matter counterparts. That might sound trivial, but in the high-stakes game of cosmic accounting, it's a potential smoking gun. The challenge: statistical significance. Current results hover just below the gold standard 5 sigma threshold needed to claim discovery. Upgrades like Hyper, with its vastly increased detector volume, aim to settle the debate by catching enough neutrino interactions to spot even subtler discrepancies. The implications are staggering. If confirmed, neutrino CP violation wouldn't just fill a textbook gap, it would rewrite our origin story. Here, how it might have worked. In the universe's first microseconds, exotic high-energy processes like the seesaw mechanism could have produced heavy neutrinos that decayed asymmetrically, spitting out more matter than antimatter. Those leftovers then annihilated with nearly all the antimatter, leaving behind the slender residue that built everything. Neutrinos, barely interacting with the chaos around them, would have carried this asymmetry unscathed through the plasma of the early cosmos, like messengers passing through a battlefield untouched. What makes this theory so compelling is its testability. Unlike dark matter or string theory, neutrino CP violation operates within reach of current technology. The deep underground neutrino experiment in the US will soon join the hunt, comparing neutrino and antineutrino oscillations over an 800-mile baseline with unprecedented precision. Its liquid argon detectors can reconstruct interaction details down to the atomic scale, potentially spotting CP violation patterns too subtle for other experiments. Combine that with Hyper-K's sheer neutrino-catching power, and we might have definitive answers within this decade. Yet the puzzle has deeper layers. Even if neutrinos are guilty of cosmic favoritism, they can't shoulder all the blame. The observed CP violation in quarks, the building blocks of protons and neutrons, is orders of magnitude too small to explain the matter surplus. Neutrinos might be part of a larger conspiracy involving yet undiscovered particles or forces. Some theories propose that neutrinos and their hypothetical sterile partners engaged in a primordial seesaw, leveraging their mass differences to amplify matter's advantage. Others suggest lepton asymmetry, an imbalance in ghostly particles like neutrinos, got converted into the baryon asymmetry we see today through processes called transitions, essentially transferring the cosmic ledger's imbalance from one particle family to another. The beauty of this detective story lies in its universality. Every atom in your body is a survivor of that ancient mismatch, a descendant of particles that outmaneuvered annihilation by the slimmest margin. Neutrinos, often dismissed as cosmic afterthoughts, might hold the ledger documenting that narrow escape. Their oscillations aren't just quantum quirks, they could be echoes of the universe's first and most consequential accounting error. As detectors grow more sensitive and models sharpen, we're not just chasing abstract physics. We're tracing the lineage of existence itself, one ghost particle at a time. Neutrinos aren't just particles, they're portals to the universe's strangest possibilities. While most scientific discoveries fill gaps in existing theories, neutrinos keep pointing to gaps we didn't even know existed. Take sterile neutrinos, a hypothetical fourth flavor that wouldn't interact with matter at all, not even via the weak force. These phantoms of the phantom world could solve two mysteries at once: the perplexing anomalies in neutrino oscillation data and the identity of dark matter. Experiments like Mini-Bueni have recorded more electron neutrinos appearing than standard models predict, as if some unseen particle is meddling with the results. If sterile neutrinos exist, they'd oscillate with known flavors just out of view, like a shadow dancer slipping between spotlights. The implications: a hidden sector of particles operating parallel to our own, invisible yet shaping the cosmos. Then there's the tantalizing connection to magnetic monopoles, theoretical particles that carry just a north or south magnetic charge, unlike everyday magnets with both. No one ever found one, but neutrinos might be the key. Some grand unified theories suggest monopoles could leave trails of distorted spacetime as they move, creating neutrino-like particles called monopole-catalyzed neutrinos. These would carry bizarre energy signatures, potentially explaining ultra-high energy neutrinos detected by IceCube with no obvious source. It's a cosmic detective story where every outlier in neutrino data could be a breadcrumb leading to physics beyond. Even quantum gravity gets a neutrino twist. Theories like loop quantum gravity predict spacetime has a granular structure at tiny scales. Most particles are too bulky to notice, but neutrinos, with their feather-light mass and interstellar travel, might accumulate subtle delays if spacetime isn't perfectly smooth. The ANITA experiment in Antarctica detected 2 anomalous neutrinos seemingly coming up through Earth instead of down from space. While likely explained by conventional physics, a fringe hypothesis suggests they could be relics of quantum gravity effects warping their paths through the planet. It's a long shot, but neutrinos have made skeptics eat their words before. Perhaps wildest of all is the idea that neutrinos could be particles, entities that are their own antiparticles. If true, it would mean every neutrino is simultaneously itself and its own mirror image, blurring the line between matter and antimatter. Experiments like Legend in Italy hunt for this by searching for an ultra-rare nuclear decay called double beta decay, where neutrinos effectively vanish into themselves. Success wouldn't just rewrite particle physics. It could explain why the universe favors matter, solving the antimatter mystery in one stroke. What unites these exotic pursuits is neutrinos, unique resume. They're massive enough to feel gravity yet quantum enough to tunnel through dimensions, elusive enough to hide secrets yet detectable enough to tease us with clues. Every anomaly in their behavior, whether a missing oscillation or an unexpected energy spike, is like a crack in reality's facade, hinting at a grander structure behind the curtain. Future detectors like Dune and Juno will turn these cracks into doorways, probing whether sterile neutrinos, monopoles, or quantum gravity leave fingerprints in neutrino data. The universe's quietest particles might soon become its loudest revolutionaries, whispering truths too strange for our current physics to contain. Every second, trillions of neutrinos from the sun and cosmic rays pierce through your body like you're made of mist, passing through flesh, bone, and even the iron in your blood without a single collision. It's a surreal thought. These ghostly particles outnumber the atoms in your body by 1,000,000,000 to 1, yet their presence is so intangible you'd never know they were there. From a physics standpoint, they're utterly harmless. The odds of a neutrino interacting with your body over an entire lifetime are slimmer than winning the lottery while being struck by lightning. But here, where things get interesting, despite their near-total indifference to matter, a handful of scientists and philosophers dare to ask, could these cosmic phantoms influence life in ways we haven't yet imagined? The numbers seem to shut down any debate before it starts. For a neutrino to interact with an atom in your body, it would need to hit the bullseye of an atomic nucleus with precision akin to threading a needle from 1,000 miles away. Even then, the energy deposited would be less than a mosquito whisper. Yet history teaches us that dismissing ideas because they defy conventional odds can be short-sighted. After all, quantum tunneling, where particles bypass barriers they shouldn't, was once considered impossible too. Some researchers speculate that rare neutrino interactions could subtly alter DNA or cellular processes over deep time, acting as a weak but persistent evolutionary nudge. It's a fringe hypothesis, but not without precedent. Weak nuclear forces, the same ones governing neutrino interactions, already play a role in enzyme reactions within our cells. Then there's the consciousness angle, a theory so speculative it straddles the line between physics and metaphysics. A small group of theorists, like physicist Roger, have pondered whether quantum processes in microtubules, tiny structures in brain cells, could be influenced by external particles, including neutrinos. The idea is that these particles might introduce quantum-level noise, potentially affecting neural decision-making at scales too fine for current tools to measure. Critics rightly point out the lack of evidence, but the underlying question lingers. In a universe where particles can exist in multiple states simultaneously, can we definitively rule out subtle influences from the cosmos's most abundant yet elusive particles? What makes these ideas compelling isn't their likelihood, it's their challenge to our assumptions. Neutrinos have already shattered expectations by oscillating, carrying mass, and possibly shaping the universe's matter-antimatter balance. If they've rewritten physics textbooks before, why couldn't they surprise us again? The deeper truth is that neutrinos force us to confront how little we understand about the intersection of quantum reality and biological complexity. Every second, these cosmic ghosts write trillions of untold stories through your body, their passages as silent and enigmatic as the universe itself. Whether they're mere spectators or silent participants in life's grand tapestry remains one of science's quietest, most tantalizing maybes. Imagine trying to find a single unique snowflake in a blizzard. That's the challenge neutrino hunters face daily. But now, artificial intelligence is handing scientists the ultimate cosmic magnifying glass, transforming how we spot these ghostly particles. Deep beneath mountains and ice, detectors capture petabytes of raw data, flashes of light, streaks of energy, and countless false signals masquerading as neutrinos. Traditional analysis methods, painstakingly crafted by physicists, can only sift through this deluge so fast. Enter machine learning, algorithms trained to recognize the subtlest fingerprints of neutrino interactions, filtering out cosmic noise with superhuman precision. It's like teaching a neural network to distinguish a whisper in a hurricane. The magic lies in AI's ability to spot patterns humans might miss. Take IceCube's Antarctic Observatory, where sensors buried in glacial ice capture fleeting bursts of radiation, the telltale blue glow left when a neutrino finally interacts. Early detection required manually calibrating what a real signal looked like, a process as slow as it was imperfect. Now convolutional neural networks, the same tech behind facial recognition, scan IceCube's data in real time, identifying neutrino events with 99% accuracy. These algorithms don't just match predefined templates, they learn from millions of simulated and real interactions, spotting anomalies that could hint at new physics. When a high-energy neutrino from a distant blazar lit up IceCube in 2017, it was AI that helped trace its origin within minutes, turning what once took months into a cosmic game of instant replay. But AI's role goes beyond speed. It's uncovering signals too faint for human-designed filters. At the Super Detector in Japan, machine learning models have resurrected lost neutrino data by identifying faint interaction trails previously dismissed as noise. By analyzing the precise timing and topology of photon hits in the detector's water tank, these algorithms can reconstruct neutrino paths with subatomic precision, even when only a handful of photons are present. It's akin to restoring a blurry, underexposed photo to crystal clarity using computational wizardry. Projects like these have boosted Super-K's effective sensitivity by 30%, effectively adding years' worth of data collection overnight without digging a single new tunnel. The most exciting frontier, AI is teaching us to ask questions we didn't know to ask. Researchers use unsupervised learning, where algorithms find hidden patterns without human guidance, to scour neutrino data for unknown unknowns. In one experiment, an AI flagged a cluster of peculiar events that didn't match any known neutrino interaction. Instead of dismissing them as glitches, physicists realized they'd stumbled upon a rare form of neutron decay, a process previously only theorized. This symbiosis of silicon and science is creating a new kind of discovery pipeline. Instead of testing specific hypotheses, we're casting a computational net wide enough to catch surprises the universe didn't announce. Critics argue that AI's black box nature risks obscuring the physics behind neutrino detections. After all, trusting a neural network's verdict without understanding its reasoning feels antithetical to scientific rigor. But teams are tackling this head-on with explainable AI techniques, like attention mapping that highlights which detector features influenced each decision. The result is a collaborative dance. Humans guide the AI's training with physical principles, while the AI reveals nuances that refine those very principles. It's not replacing physicists, it's giving them superpowers. As next-generation detectors like Dune and Hyper come online, their AI systems will face data tsunamis dwarfing today's challenges. Dune alone will generate the equivalent of 10,000 HD movies worth of data daily. Without machine learning to parse this flood, breakthrough signals would drown in the deluge. But with algorithms evolving alongside hardware, we're entering an era where neutrinos won't just be detected, they'll be interrogated. Every oscillation, every flavor shift, every whisper from a supernova will be cross-examined by silicon minds capable of seeing deeper into the quantum fog than any human ever could. The ghosts of the cosmos are finally meeting their match. Neutrinos have spent most of scientific history as cosmic afterthoughts, shadowy particles dismissed as too insignificant to notice. Yet today, they've become the universe's ultimate, revealing secrets from the birth of stars to the fabric of spacetime itself. Every time we think we've pinned them down, they slip through our fingers again, leaving behind tantalizing clues that point to something bigger. Whether it's their role in supernovae, where they carry away 99% of a dying star's energy, or their potential connection to dark matter and extra dimensions, neutrinos refuse to play by the rules we've written for them. And that's exactly why they matter. The irony is delicious. The universe's most elusive particles might hold the answers to its grandest questions. Take the Matter-Antimatter imbalance, a puzzle that's haunted physics for decades. Without a slight asymmetry favoring matter over antimatter, the cosmos would be an empty void. Neutrinos, with their mysterious oscillations and potential CP violation, could be the missing piece. The subtle cosmic cheat code that allowed galaxies, planets, and life to exist. Or consider dark matter, the invisible scaffold shaping the universe's structure. If sterile neutrinos, hypothetical heavy cousins of the ones we know, are part of that shadowy realm, it would mean these ghost particles have been pulling the strings behind the scenes all along. What makes this moment so electrifying is the technology finally catching up to the mystery. Detectors like Hyper and Dune aren't just upgrades, they're quantum leaps, capable of spotting neutrinos with precision that would seem like magic a generation ago. Hyper-K's colossal water tank, large enough to hold a skyscraper, will capture supernova neutrinos from across the universe, while Dune's liquid argon chambers could catch the faintest whispers of CP violation. These experiments aren't just tools, they're time machines, letting us peer into the first seconds after the Big Bang or witness the death throes of stars millions of light years away. But the real thrill lies in what we haven't predicted. Neutrinos have a habit of us, first with their existence, then their mass, then their shape-shifting flavors. The next revelation could be equally disruptive, evidence of extra dimensions, cracks in the standard model, or even a connection to quantum gravity. Every anomaly in the data, every unexpected blip in a detector, could be the first hint of a reality stranger than we've dared imagine. So here's the beautiful truth. We're all part of this detective story. Every time you feel sunlight on your skin, trillions of solar neutrinos are passing through you, unchanged since they left the sun's core 8 minutes ago. When you look up at the night sky, neutrinos from distant supernovae and black holes are streaming through your body, carrying tales of cosmic violence and creation. You'll never feel them, but they're there, silent witnesses to the universe's grand narrative, and now, finally, we're learning to listen. The hunt for neutrino secrets isn't just for physicists in lab coats. It's a reminder that curiosity is humanity's superpower, that the drive to ask why can unravel mysteries hidden in plain sight. The next breakthrough might come from a detector buried under ice, a mine shaft, or even a theory scribbled on a napkin. But one thing's certain, the universe's quietest particles still have the loudest stories to tell. So keep looking up, keep questioning, and stay amazed. After all, the greatest discoveries often start with the things